Welcome everybody to this episode of Simulation Century, where I'm really excited today to have our guests who are admiring all of the issues we have with Earth science and really pushing the envelope for in the simulation century for how do we do data enriched science, but also now add AI into what Dr. Christa Peters-Lidard here is calling the fifth paradigm. And we'll also be talking to our good friend, Dr. Jeff Arnold from Interion about his background working with the EPA and with NOAA and looking at all of the Earth observation data. So again, welcome you guys. And why don't you just start off by introducing yourself? Why don't you go first, Christa?
Sure, thank you. So my name is Christa Peters-Lidard, and I am a hydrologist by training. I spent 24 years at NASA's Goddard Space Flight Center, where I worked my way from the Hydrological Sciences Laboratory up to the Director of Sciences and Exploration. But really my core background and some of my most important work has to do with doing estimating the water cycle using land surface models and techniques known as data assimilation. So I'm excited to talk about how that work has evolved in the age of AI and what the potential is for learning about the water cycle through Earth observation, models, and simulation.
That's fantastic. This is going to be a great session there at Mod Sim World at the Simulation Century's 15th annual event. We also have with us Dr. Jeffrey Arnold. Jeff, what are you going to dazzle our audience with this year?
Hey, Richard, thanks for having me. I'm Jeff Arnold. I lead innovation work at a company called Interion Corporation, and we do science and Earth system science analysis and support to federal agencies. So we do a lot of work supporting the deployment of sensors on satellites and also at the surface. And we then produce science packages out of those data and use those to try to inform decisions and actions that federal agencies take to try to ensure that we can continue to deliver the kinds of services that folks in the United States expect from federal agencies and make decisions as the environment that we're in now continues changing so fast. A thing that I'm excited about talking about here is how the introduction of additional AI capabilities and machine learning applications have really changed the kind of work that I used to do when I was doing science full time. And that's atmospheric science and a lot of work in the planetary boundary layer, right down where the humans are breathing and trying to figure out what's new about science that we can learn by building data models and understanding those models in the terms of how we can look for places where we need to write some new physics, where we need to understand things that we haven't been able to see before until we got the ability to interrogate those data. So I'm really looking forward to the session, Richard.
This is really going to be exciting, and I've enjoyed getting to know both of you as we're heading towards this event. As most of you know who are following this Simulation Century event and the podcast, the thesis of our event is that the last century was about the moving image. And our friend from Canada, Marshall McLuhan, would say that in the last century, the way we communed around major events like the fall of the Berlin Wall or the Vietnam War, whatever it was influenced by the media we used to commune around those events. So, and back then it was the moving image, right? And McLuhan would say that, or did say that, it changed us physiologically, sociologically, and really affected our society. And we say now this century is about simulation. It's the first time when we can take digital data from all over the world, and that's what both of you have been doing to great effect over the last all of your careers so far. And we're in this incredible inflection point where now we can have AI and simulation help us not just reflect on the past events, but really look at what's happening today, as we were all today looking at the smoke that's coming down from Canada and the layers of it across the United States, and what does that mean for air quality and science. But now also, how do we use that capability to predict the future? And I always say the highest moral purpose is how do we actually create the future that we want using these powerful capabilities. So Christa, when I first learned about you, I'd seen your Maniac lecture back in 2018. So this is before generative AI. And even then you were talking about, your progression and how, all of your childhood dreams had already come true. So what's going to be next? So I'm interested to hear about that. And I'm sure we'll talk about that in this session, both in this podcast and at the event. But you talked about the fourth paradigm and how excited you were then and what it meant for science even before generative AI. Can you talk about what the fourth paradigm was all about?
Yeah, sure. So, yeah, Richard, as you all will see if you watch my Maniac talk, I mean, I grew up wanting to be an earth scientist, and I grew up wanting to work at NASA, and that all happened. And as I was working at NASA, one of the things that I started to realize is that we had so much data. And so the first kind of realization is that, combining the models and the data was required in order to enable the kind of prediction that would make the data useful. And, to your earlier point, right, that, the higher purpose, being able to predict where famines are going to be, where drought might occur, how it might recover over time, where floods, landslides, you name it, right? So we sort of moved, into this data intensive third paradigm of science while I was at NASA, right? We started bringing it all together. And then we started to realize that the models were not able to predict as accurately as one would hope. And when you started to really confront the models with data using formal benchmarking, you learned that there were information gaps, and that that process of actually confronting the models with the data and using that as a hypothesis driven testing methodology to advance the science. So that's really what moved us into the fourth paradigm, was being able to, there was a famous experiment in land surface hydrology called Plumber, and it kind of rocked my world because it was about land surface models.
Brilliantly named, sounds like.
Yeah, and really, what we learned from it was that a simple data-driven model, which in this case was a regression model, could beat most of these super complex, physically based land surface models to get the fluxes, meaning the latent and sensible heat flux partitioning, correct for land surfaces. And this really threw us. I mean, we had spent 15, 20 years developing these land surface models. And so, that's when I think between that and then, I worked with some papers, especially with one of my colleagues, Gray Nearing, who's now at Google, to really move into this formal benchmarking framework. And that's what grew, this fourth paradigm for me, was that everything we've learned to date, starting from learning from the data and then getting encoded in models and then using large data sets, suddenly we were confronted with the fact that there's still missing processes. I think one of the hallmarks of hydrology is that you can't observe most of hydrology because it happens in the subsurface. So I think, that's when my worldview changed, that we really had to approach this in a different way. And that's what kind of grew towards this fourth paradigm for hydrology.
So we're going to go from there to the fifth paradigm. And you just told me earlier that there's a NASA paper about the sixth. So we'll get to that in a second. But yeah, it's occurring to me that what's so interesting about this conversation is that, Christa, you've spent your career kind of looking deeply at the world from the soil all the way, up from there, looking at the hydrology of the earth. And now, Jeff, you have been looking at the atmosphere down, right? So we have this complete picture now. So talk about some of your experiences with at the EPA and at NOAA and places like that, and where you think we are in this paradigm shift.
Yeah, that's great. And when I was a federal employee, when I was working for the Department of Defense, Christa and I actually overlapped, and so we were doing some work in my program with some money from NASA to try to look exactly at this interface, Richard, because as you know, all of the excitement in science happens at the interface. And so, as Christa was already talking about how important it is to be able to characterize the subsurface flow in hydrology, the interface from where the precipitation comes in, where the heat comes in from the atmosphere, and all of that interaction right at the interface is really, really, it's better described now than it ever has been, but it's still pretty poorly described. And it's only well described in places where we have a wealth of observations. And so what we'd really like to have, and I think one of the places where we could make a huge, huge advance in the next 10 years or so would be to try to look at reliably and believably simulating this subsurface hydrologic forces and this interface where what we call the planetary boundary layer, where all of these fluxes that Christa mentioned, where all these fluxes are happening. And if we could simulate that reliably and believably, then it would unlock the ability to make use of lots of things around predictive agriculture and around things that we could use for building this data fabric in places where we don't have observations, where we could use some of the work that Christa mentioned, Gray Nearing at Google, who's been doing some terrific work on machine learning, on starting with machine learning functions to try to describe hydrologic flows, which we previously used. Basically, you would start with F equals ma and derive everything you needed and try to represent those equations numerically and have a high performance computing network solve those for domains. And those domains had to be very small so that you could have them complete in a fast enough time, even on the fastest computer networks in the world at the time. And those have been expanding, but what machine learning does is allow us to make not just a single run in some period of time, but hundreds or now even thousands of runs to build a very, very large simulation ensemble. And we can learn so much more from these ensembles. And so I think what we really need to look at, again, the place that I think that there's real benefit to be derived is looking at this place where that the subsurface hydrology up to the surface water hydrology and to the atmospheric chemistry in the boundary layer. So if we can describe that in a way that's believable, then we can go places where we don't have any observations at all in sub-Saharan Africa, and places where we only have even pretty sparse satellite coverage, and we'll be able to do a much better job of informing decisions and actions that can really ease suffering and increase the productivity and the real livelihood of folks now who might otherwise miss out on things that the AI revolution is going to bring.
That's fascinating, and yeah, this is causing so many sort of synapse firings for me. And if you guys have seen any of my podcasts in the past, you know that I tend to go down these like tangential rabbit holes, and I'm going to do one very quickly with you, so bear with me on this for this ride. But I'm just thinking, Christa, about this fourth dimension place where we were, and I'm just thinking how different it was, the whole world was in 2018, and all of us. And I'm not going to ask anybody's ages, but I'm up, I just crossed the 60 barrier. So I'd seen a lot of changes in my life, in science and compute and everything. Everything's different now. We have cars that drive themselves. We produce perfectly spelled documents without knowing how to spell, all of this stuff. But in 2018, we were at that point where, I believe the reason we were able to actually marshal some resources scientifically and react and respond to that pandemic event was because of the fourth paradigm. It's the ability to have really rich data sets and have these models where we could run simulations and determine what we needed to do in the physical world with our science in order to make those retrovirus or those the mRNA vaccines. And now we're at this point where we have AI, which really happened, what was it, in December of 2023, right? 2022. That was that bump in the night when everything changed, everything shifted, and my phone was blowing up with people telling me, like, have you
Mm-hmm.
seen what's happened? So now
Mm-hmm.
we're wrestling with that and we're trying to put it to good use.
Mm-hmm.
What's changed most dramatically for you, Krista, from 2018 to today in 2026?
Well, I think a couple of things, right? I mean, so, in hydrology, we've been using different machine learning techniques for decades. We calibrate our models because again, as I mentioned earlier, we don't observe most of the hydrologic cycle, right? So when rain falls on a given location, how it gets translated into runoff depends a lot on the soils and the properties of the soils, which you don't know. And so, there's been a lot of, you know, data-driven calibration, as it is called in hydrology. But what's changed is that now the data-driven models beat anything that we can do. So there's LSTM, there's physics-driven LSTMs that predict runoff at on multiple day timescales better than the best hydrologic models we have. And so, what's changed is that we've now come to realize, I think we've all sort of learned, in some ways it's like the bitter lesson, right? We've spent all this time on theory and trying to encode theory in the models, but that theory isn't beating the purely data-driven models as hard as we try. So that must mean we need new theories. And so I think that's what's really changed, is that, just it's the same way that the benchmarking rocked our world. Now these data-driven systems, with the transformer architectures, are beating everything that we're throwing at it with physics. I mean, we've spent lots of time optimizing code, getting it to scale on like massively parallel compute systems, and more resolution doesn't solve the problem, because ultimately there's something wrong with our understanding. And so I think that's where we are now, is that we are now moving towards hybrid systems that use emulators for the parts we don't know well, and that still have some physics embedded in them, but we can blend these two things together to move forward, not only for computational reasons, but for, better prediction. And so that I think is the biggest sea change. I mean, we've got so much data now. I guess that's the other big sea change, is that before we were somewhat data limited. In Earth observation, the entire landscape has shifted to having multiple private vendors in addition to the large government backbone. And so now, not to mention nonprofits, right? Methane sat and other things, right? So now we're going to have a hybrid architecture of Earth observations that we can apply to these problems, but we have to apply them in a way that recognizes that we don't know all the physics like we thought we did. So that's kind of where my mind is.
I think that's fascinating. And that's something we've held in, even when I first started working with machine learning back in 2009, and afterwards, we got to this point where we said, don't do anything without asking for a machine perspective, because sometimes the human expertise can run into these sort of epistemic closure spins where they're just like, well, you can't do that because I've never been able to do that before. When you take a machine intelligence, and I've got one example about the F-35 helmet when I was at Lockheed, where everywhere we went, it was almost like the iPhone, how do you get glass to go to the edge of the iPhone? And everyone said it's impossible, it'll be too brittle, it'll break. We had the same issue at Lockheed with the F-35 helmet, where we wanted a 180-degree or a field of view, and everyone said it can't be done. So we turned it over to an AI, and with its perspective, it looked at the problem from multiple dimensions, came up with a different perspective. None of the experts we had, and we had lots of experts, it never occurred to any of them to use plastic Fresnel lenses from lighthouses, and layered in, they gave us the ability to do that. I mean, it's a longer story
Wow.
than that, but that was one of those aha
Yeah.
moments for me.
Yeah.
Jeff, what's like the biggest, what's dramatically different for you since the bump in the night of?
Yeah, that's such a good question. And I'm going to pick up right on Krista's point. And I think for me, the most important thing about what she was describing, and the most important thing that's happened across my career, and it's been accelerating in the last 5 years, particularly, has been the demonstration that of what Krista was actually saying was it's never been just data or just the model. The way we get better is by data and the model together. And what artificial intelligence and machine learning allow us to do is put them together in new ways and in many, many more ways than we've ever been able to do in the past. And so it's the great thing about interacting with kids, I still call them kids, who are in graduate school now, and training them up because we got to train them differently because they're working in a very different kind of environment. And so they the day of being a scientist where she works alone at a laptop somewhere and produces, those things were gone even when Krista and I were in school, and people were already working in teams. And now those teams have just been augmented by silicon agents. And so what we're doing is moving from human teams even to these augmented teams. And a person will come in and not be writing code from scratch, but they'll be building ingestion routines to be able to kick off maybe hundreds or even thousands of simulations that'll run while they're doing something else the rest of the time. So we need them to be able to still have a feel for the physics of the model. And I think it's so important for Krista to have pointed out how there are places where we're finding, because of the way we put models, formerly numerical models, together with the data, we're finding places where our physics is breaking down. And so that means we've got to generate some new physics. We can't just collect data and answer all the questions that we want to answer. We're definitely going to have to build some new physics. And that's some of the most exciting work. And I think this is another thing we've got to focus on, schooling up the intuition of the new folks coming through graduate school so that they can get a feel for when the physics represented in the model are incomplete, and then go off and think more together with the model and with AI agents, think about how they can start filling those gaps. And that change really in the representation of the scientists and the scientist teams, and the way scientist teams interact with data and models is really, and I guess this, Krista, is a lot of what your new paradigm is talking about how humans and models interact together. And I think understanding that it's not just using imperfect data to try to assimilate into an imperfect model, but using the model to tell us where we don't understand pieces, and then helping us focus on those pieces so we can write better physics is super interesting.
Yeah, you've triggered a couple of mantras there that are in, I'm pointing in the right direction, my book here. But, one of them is my favorite Alan Kay quote is, "Perspective is worth 80 IQ points." But now we have the machine perspective as a new addition. The other is that it's insufficient today to be a standalone human being in all sorts of endeavors, radiology to, certainly in science. If you're unaugmented, there was a time when we said someone who was adept at search using the internet was arguably more capable or more intelligent than those who were not, because they got to answers more quickly. We can argue whether those answers are correct or not, but now, and then the last one is, the critical issue for the century, certainly in science as well, is getting the right balance between humans and machines to optimize the outcome, whatever you're trying to solve for. And it's about human and machine effort, intelligence, and attention, those three things. And if you get that balance right for whatever you're pursuing, you get, you outperform and become, get superhuman results. I want to shift now to the one of the issues of AI and also the opportunity for transparency in the models and in the data. Because some of the stuff I've seen you're working on there at Interion, I think is really exciting, Jeff, where you're able to not only say, yes, we have AI that's performing functions on all of these massive, massive petabyte-sized data sources, but now I can, the ability to actually drill all the way down and say, how good is that data? Then above that, how good am I using the right models? I mean, thinking about weather prediction or whatever it is, that's the real conversation. And I think, even during the pandemic, not to keep harping on the pandemic, but it was driving me nuts seeing people standing in front of podiums, whether it's a governor or a mayor or a president, talking about their gut instincts, what they felt ought to be done, when the conversation really should have been, as it always has, around, well, here's the data we had that we were making a decision on. Here's how we modeled it. And you can argue about how good is the data or how good are the models, but stop looking at me, shift your cameras and your microphones and everything over to this system that we're using to inform the decision. How are we doing on the transparency front in terms of where AI is maybe altering the scientific method in a way that may be causing some concern for either of you?
Yeah, I think back to the I'll just start with the question of weather, and then we'll try to get up to a little bit concerning. I mean, I think a little bit, as I've said earlier, a little bit that what AI can help us do is learn faster where our data and physics are short. And in the current transition period that we're in now, I'm a little more concerned every day that people are overselling where we are now with the data and physics that we have, and that some people can claim to have resolution. And as Christa already said in at the top of our podcast here, that better resolution doesn't fix the problem if your physics are wrong. And so I'm a little concerned in some cases that we're overselling the speed aspect and the kind of intuition that looks like we're getting from artificial intelligence, which may not be built on a very firm foundation. So I think about that around weather because that's what I think the most about, but it's also because weather has made very fast progress in the last 5 years of coming down in scale and looking at questions of how much better we can drive the forecasting. But I'm concerned about this. Some folks have called this the asymmetry in speed of trust. And so that at the moment we have this outrageous trust in the machines because they're so fast, and because as we were talking about earlier, you can create very large ensembles, and so you can build much better error bars, and your PDFs are more confident, and so you've got what you think is a better interpretation, but you've built it off of these same gaps that have led us to have these breakdowns that Christa was talking about, that we've known about since Plummer. And so this speed of the machines, which is leading us to put too much trust in the machines at a time when we are still moving basically at the crawling pace of humans in not only thinking about things, but with our regulatory structure as well. So how do we build these models which can then reach out and draw in all of these petabytes of data which are widely dispersed now? How do we open that up as humans and think about how we can better support the production of models and model data hybrids to support folks who are not going to be able to make use of, not in places where they can make use of these really dense data fabrics. So I think we need to we need to concentrate more on the interface from the very fast machines and the slow-moving humans on both the cognitive side and on the regulatory side, so that we can address this asymmetry. So that without that, I feel like we'll be in the blind trust of the models, just counting the billions and now even trillions of weights which go into the models, and thinking that we can explain them everybody's looking for explainable AI, thinking that we can explain them just by looking at the weights, but looking at the weights is not going to explain it. We have to build in physics safeguards around it so that we can interpret those. So that's the thing that's got me most concerned about where we are in this transition period.
What about you, Krista? Are you,
Yeah.
I've seen a bunch of stuff recently about concerns about AI contagion in scientific research papers. But what are you seeing in
Yeah.
your field?
Well, so I think let me start with hydrology and earth science in general. I mean, there's some canonical problems with uncertainty characterization and communication, right? That example you gave, Richard, of people standing at the podium making a decision. Well, imagine they're standing in front of a classic hurricane forecast cone of uncertainty, right? And they're making an evacuation decision. Okay, so I mean, it turns out that the cone has gotten smaller over time, and the intensity estimates have gotten better over time. But, the decision about whether to evacuate people is really this human, information interface. And I think that is true for flood forecasting. It's true for many things that we do. And so I think that's an area where we really do need more work. I mean, I think the formalism of information theory can help us to really do a better job than we do today of either overselling or underselling, right? I mean, I think both of those things happen. Climate change, we're almost 100% certain it's happening, but yet we sort of undersell it because we caveat it to death. So, I think that is something that we need to get a handle on. I think the second thing that is happening is, when you have an agent on your team, how do you work that in the standard publication and attribution process when you submit a paper, right? You have to. So, I mean, there have been papers written now entirely through, AI-based automation of hypothesis generation, testing, and writing, right? So we know it's possible. We don't have a good model or framework for how to properly use that in an attribution sense, as well as in a reward sense, right? Because people are rewarded based on publications in the research world.
Yeah, publish or die, right? They say in the academic world.
So we're going to have to recalibrate that somehow to, you want to, one of the promises of the fifth paradigm, which is about sort of, AI automation of the scientific process, from beginning to end, that should expedite science, which is a good thing. Mm-hmm. But, the structures to be able to support that are not 100% there yet. And, we're moving out of an old model of publications that require slow peer review to, people throwing stuff up on archive without any peer review because they want to get the stuff out the door as soon as possible because it's too slow to wait 1 or 2 years for a paper to appear. So anyway, so I think there's there's like the speed of science and there's the speed of decisions. And both of those are going to require us to wrestle with this information content issue somehow. And I think that is going to be something as we move towards the fifth and even sixth paradigm, we're going to have to be able to work that out.
Yeah, one central idea that I think is probably the most powerful idea in science that we don't see in public policy and a lot of other areas today is the willingness to be disproved has to be central and core to it. That peer review, yes. that ability to challenge something. And by the way, just mapping it over to our Simulation Century audience at Mod SimWorld, it's a big component of that always that's been around V&V, validation and verification of all of the components that go into a war game or into a simulator for an F-35 aircraft. There's a whole science behind that, because if you build simulations on faulty individual data pieces, you get really, really faulty outcomes with this big, large, complex systems that you build. And I think that is no more important than it is in science. It's incredibly important there. And I know, at Interion, Jeff, you guys have been adhering to a lot of the stuff we've been talking around what we call an epistemic airlock, which means the minute you bring AI into any system, and it at some point a human has collected a lot of data, or the AI has collected data, then it's been AI mediated, it immediately should go into that airlock and not come out and go back into the body of information until it's been some level of human peer review. And I think we might get to a point where there's also machine peer review. And I'll just map that back to my Lockheed times to say that I think you guys know this, but when you have an autopilot on an aircraft, there's never just one. There shouldn't be one. The ones we built at Lockheed anyway, there were always three. And ideally, they're built by different people and put together. And they have to agree with each other if they're going to do anything abrupt or change of course or whatever. And when they don't agree, they got to call the human to come in. So you have the judge and the critic and I see that in Interion and some of the science stuff you're doing, you've got the judge and the critic and these different AI components that can really try to do that challenge of anything that's been AI mediated, along with the humans trying to do it as well. But
that's right.
What do you?
Yeah, that's right, Richard. That we're not at a point yet where we can take the human entirely out of the loop, and we're not I don't think we're ever going to be at a point where we want to take the human entirely out of the loop. Even as we're working to reduce this speed of trust asymmetry, we've got to be able to build these interfaces so that we can still work at human speeds to understand those products that come out. We do a lot of support, as both of y'all know. Interion does a lot of support to NOAA and NASA, for example. And one of the things we want to make sure is that for any of the work that we're doing, that where we're bringing in some cases, just as you've described, where we're bringing in AI not only to generate some new ideas or new combinations of data for data analytics, that we use multiple different AI to be able to describe in more complete terms what it is that's happened, and then still have a human be able to determine whether that's something that we want to roll back into any of these existing archives of data, so that we don't do something that becomes deep down in some of these. The NASA archive of Earth observations now is approaching 190 petabytes of data and growing by petabytes a week. So it would be easy to roll something in there and have it sit like a time bomb somewhere deep inside some data stream until somebody needed it to do something. So we want to make sure we don't seed any of those problems in any of these really long established, very, very well verified and evaluated data streams.
I think that's incredibly important. The other idea that I'd love for each of you to talk about is again, going back to transparency. In logistics, we're talking a lot in the defense community about contested logistics, and even logistics in the supply chain of our critical systems, whether it's energy or whatever. Where was that part made? How did it get transported here? Can I track it using some kind of blockchain like lineage all the way back to wherever all the parts originated? How was that assembled? So we're doing a lot of that now, beginning to do it better for physical assets. But with scientific information, that also is critical. If I can go all the way back to how were those components assembled, I think in NASA you call them granules, right? Those little components, like a observation of a water temperature off of a buoy or whatever. And how did that get assembled into some higher level of understanding? How did that get then packaged up and say, well, we know this is true, so let's include that in this other research. But being able to drill all the way back into that granule to challenge it, I think is critical. Are we going to be able to preserve that kind of capability given we're in a sense of revolution where the amount of data we're pulling in is beyond human ability to track, certainly.
Well, I'll take a stab at that. I mean, I think at least within NASA, there's a strong commitment to open science, which means open data, open code, open algorithms, workflows, and full transparency and reproducibility, including the provenance, which is what you're talking about, right?
Exactly.
So how do you, so I think that is essential, and those are all critical components. In fact, they're mentioned in the paper that I referenced on the 6 paradigm as best practices for essentially a closed loop accelerated knowledge discovery environment. But I think that in addition to that, there's this question of when you're in a mode where you're trying to get insight and make changes and sort of whether it's a counterfactual analysis or whether it's some sensitivity to some new data. So I mean, I think all of these systems have to be designed with modularity and substitutability, or so at some point you want to be able to substitute a physics-based model with an emulator and data driven for other things. So I think that's all part of the process, but making that perfectly reproducible is hard. We just even like saving all of the configurations for your experiments. I mean, they do this every time they do one of their, climate, the IPCC reports, which depend on CMIP, these, climate model intercomparison projects, right? Like there's all kinds of effort that goes into configuration and, making sure that at the end of the day, it's sort of as apples to apples as it can be, to a point. But to your other point, there's this value in the ensemble. So I think that's the other part of this, is that having a diversity of, and that's what's behind our climate assessments, is having multiple models from completely different modeling centers that have a different concept about how to represent the Earth system. And that's what gives it more power. So that just like with your, autopilot systems, you need that variety, and then you look
check and
for
balance.
Exactly. And it's the convergence of evidence, which is the other part you're talking about,
Yes.
right? Where you're looking for commonalities. And we did the same thing with FuseNet, our famine early warning system network. We looked at different indicators of drought and famine. And when multiple things were giving the same signal, then we had a good sense that we were right, that something was happening. So I think that's all part of that information and uncertainty assessment, is that you need enough diversity and enough, and transparency to have the trust in these systems that the union of everything will give you a better result than any one piece.
Yeah, I think in the new provenance thing that I think needs more emphasis, and we've just come from some of my folks we're up on Capitol Hill talking to folks about AI and the things we need to be guarding against. But one of them is, like I said, anytime something has been AI mediated, it should literally raise its hand and say, I've been touched by AI. So
Yes.
Now you can have a different lens when you look at it. It should have
Yes.
more questioning, not more acceptance, until it proves that it is good and it performs well against reality. But what would you add to that, Jeff?
Oh, I think that's really complete. The thing that I think is going to really help out as we're working through this transition, and I think what Christa and I have been talking about a little bit, is how exciting it is to be in the transition, but it's going to be messy for a little while longer, because we're at this stage where the asymmetry is so high, and we're figuring out ways to try to address that. I think that so long as we can remember that what we want are these emulators, as we've talked about in a couple of times, emulators, but also any of the large models that go into creating these ensembles that we've talked about. that these need to be stress tested against actual edge cases that are known, and then
Yes.
wrap those into these physics-informed constraints so that we're not using just data-driven models, which can wander. I mean, the numerical models will also wander after a time, but we have a feeling for what that looks like and for where those limits are that we don't have for the data, because we can't see into what the emulators are actually doing, because can't read all trillion weights, and so we can't really figure out what's happening. We're getting better at understanding that. But during this transition, I think the important thing, and a lot of what Chris and I have been talking about, is the need to make sure that the data scientists are paired up directly with the physical scientists, so that the people who have taken the data and therefore understand which data go together and which data can follow the other ones. Because the thing about the observations is they'll never tell you how they got to where they are, and they won't tell you where they'll be next. But you can answer both of those questions if you instrument the model correctly. And then you want a field of those observations to be able to use to be able to evaluate the model and see how well it's going. In some cases, you will use them different fields to initiate the model, but you need some to be able to diagnose where the problems are in the model that we've been talking about. So again, it comes back to both the hybrid of model and data and the hybrid of data science and physical scientists to be able to use those hybrid models to get to the point of informing decisions and actions faster, because we need these answers even faster.
That's fantastic. And, I'm just looking at the clock and I realize I knew this hour would fly by, and it's been fantastic because you guys are just doing such important work. I mean, but just to wrap up as we head towards this big event, both of you have worked on science in a lot of life or death situations, whether it's predicting famine, predicting floods, helping to enrich our understanding of the climate science. So hopefully we can prevent something even more existential than any one of those individual events. But what are you most hopeful about, given this marriage of machines and data and humans towards better understanding of the planet? I'd love to hear from each of you just what you're hopeful about in the next couple of years. What can we hope to see?
Yeah. I'll take a stab at it. I mean, I think, now that I'm working as a distinguished visiting scientist with Schmidt Sciences, one of the things we're really all in on is understanding our climate system, and especially freshwater. So, as a hydrologist, we are working hard to apply all of these new data and technologies to understanding freshwater and managing it sustainably for the future, which is, such a critical problem to solve. And so I'm optimistic that it's, that the union of governments, commercial, academic, and nonprofits to solve some of the Earth's most pressing challenges is happening right now. And so, having been in the federal sector for many years, sometime in academia, I mean, it's great to see this approach now where we're all working on these problems from a science-based perspective. And so that I'm very optimistic about. I think the second thing is that the landscape of data that has changed our world, and the landscape of AI that has changed our world. I mean, it's as we move towards, Gen AI, and, at some point we will be able to solve some of these pressing problems. So I'm optimistic that, as the technology improves and it's able to scale, along with the human's ability to work with the technology and use it for good, we will be able to solve some of these problems on Earth that have plagued us for many, many years. So, that will reduce conflict and be better for everyone.
Man, well, I'm glad you're leading that charge. Makes me feel better already. Jeff, make us feel even better.
That's more than I can handle, I'm sure. But the thing that I'm most hopeful about is this the fast growth in what I call insight democracy. And now there are so many more opportunities for people like for operators and for decision makers out on the ground to be able to get these outputs, to be able to have descriptions not only of what we think might happen in one location, say for flood or for drought over time, but then to be able to see a distribution of what the probabilities were that went into creating that estimate. So she can decide now how much risk she really wants to accept before she makes a decision to evacuate New Orleans or to cut 2/3 of a forest down for some reason or another, to be able to look for different changes, to be able to make these decisions that are protective of life safety. We want to be able to inform the decision makers with those, so that she doesn't have to have an HPC scale network behind her to be able to, and then wait 9 months for a bunch of climate projections to finish running.
Mm-hmm.
She doesn't even have to have a branch of physical and data scientists to help interpret things that come out. What we really want to be able to do is to push these data outputs closer and closer to the decision. And I think that we're already seeing lots of pieces of this. People have seen, I'm sure, images of folks out looking at wildfires, and they're standing there in a lot of places with iPads in their hand, and they're looking at it overhead. There are still pilotless balloons, drones that are taking samples, and that they're able to do a much better job predicting where those fires are going to go, and then helping to fight those fires at the same time. We want to move the decision makers' basket of opportunities, basket of choices, closer and closer to them in time. And it's already happening. And so that the ability to do it in the future is going to get even better. So I'm super excited about this democratizing of insight. I think it's going to be a big improvement.
I love that. That's a great note to end on. But I'm sure there's going to be a lot more when we gather together on August 18th in Alexandria, Virginia, at the 15th annual Simulation Century event at Mod Sim World. So those of you watching this, just click on the link that's there and register. And we look forward to seeing you in Alexandria and continuing this great conversation. And thank you, Jeff, and thank you, Christa. Keep doing the great work you're doing, and stay bold, brave, and benevolent, as our friend David Bray says. Thank you, guys.
Thanks, Richard.
Yeah, thank you, Richard. Looking forward to the 18th.